Alright, welcome back to episode 49, Solving Euler with Recursion. So this is the first one in the whole series here, and we looked at it in episode 48, and we decided it was maybe not very optimal, so we're looking back at it again to see another pure functional way of solving this problem. So we will keep our is multiple from the episode 48, which is just a little helper, returns a Boolean. Given two numbers, it'll determine whether one is a multiple of the other. And then that's where basically everything from the episode 48, that's the only similarity, really. Well, that and the final answer. So what we're going to do is we're going to modify this 3 or 5 multiple. So in episode 48, we took a number and we returned a Boolean. But you notice, in this case, that's not what we're doing. We're taking a number and we're returning a number. Because ultimately what we want to do is to find the sum of all the multiples of 3 or 5. Well, now here's something that's pretty interesting. And it'll be your new vocabulary word for the day if you don't already know it. For numbers over addition, because sum is dealing with an addition, they form what's known as a monoid. And a monoid is basically a way of taking, a monoid is always some operation for some type. And in this case, the reason that numbers form a monoid over addition is because we can take a number and add that to another number, and we still receive a number. So it's returned the same thing. Lists with append can be a monoid. So if you take one list, you can append another list to it. Another thing that's necessary for a monoid is to have what's known as an empty. And that's basically a way of saying, let's look for addition for numbers. Addition for numbers, if you add 0 to something, it's like not doing anything. And that's the whole concept of empty. So if we were to append one array to another array, the empty would be just an empty array, and it would actually have no effect. So we're going to take advantage of all of that. Now, we don't have to define any of that. This is like the ultimate type class because it comes from math and it just works with all of our arithmetic and numbers. So we don't have to do anything special for that. Right? This is something you've probably known for a very long time, is that if you add 0 to anything, you get back whatever the anything was. So, say all that to say, if we call 3 or 5 multiple and we pass 12, we get 12. If we had passed 11, then we would get 0 because that's what we would return. So now we're going to take advantage of this monoid. And the way that we're going to do that is going to be by using a recursive function that we're going to call solve. This looks very similar to our other recursive functions. So we'll have an n, which is some value. That's the thing we're going to solve for. And then we're going to have an accumulator, and we're going to default it to 0 because we want to sum from 0. And so if n is 0, then we're just going to return the accumulator. And that's our failsafe. That's making sure that we don't have an infinite loop, basically. If n is not 0, what we're going to do is we're going to recursively call solve. This is the same function here. We're going to call it again, and we're going to take n and we're going to subtract 1 from whatever the current iteration through this recursive function is. But then, what are we going to do for the accumulator? So the accumulator, the first time we call it, is going to be at 0. So, what will happen is we're going to use the fact that we're dealing with numbers here and addition to know that we're in our monoid here. This is a monoid, so we can deal with this 0 and know that we're not going to modify whatever that value is if the 3 or 5 multiple returns 0. So we can take our accumulator, we can add it to whatever our 3 or 5 multiple returned for n minus 1. Well, the n minus 1 thing here is kind of interesting, and the reason that it's n minus 1 is because this thing says the natural number's below 10. So if I didn't do that and I was solving for 10, then the first time through it would try to solve for 10, which is not actually valid for this. A few different ways of solving that, but in this case, we're just iterating through it and saying, I'm just performing the 3 or 5 multiples on n minus 1. And so it'll come back in again, it'll call solve, and in this case, the first time it would be 10, and then the second time it would be 9, and etc. until n got down to 0 as it was being called. And so if we run this and we solve for 10, we get 23, which is what we'd expect. Then we can solve for 1,000, and we get the value that we would expect. What's interesting here is we're only, quote, iterating through a list or a stream once. In other words, n is only ever 9 once. We don't have to create a list and then iterate through that list multiple times like we did in yesterday's episode. Now, one of the questions that always comes up is, well, JavaScript doesn't have tail calls, so optimizations. And if you don't know what that is, just it's not a big deal. But that's always something that everyone asks is this optimized? Well, with this accumulator here that we're passing, we are in fact optimizing it. If we didn't pass this accumulator, what would happen is that we would actually build up this huge stack trace, and we could eventually, depending on however many stack frames that you could actually put in memory with whatever the browser is going to let you, you could run into an issue. But in this case, we're actually dealing with the fact that we are passing this accumulator through. We're threading this accumulator through, and so we have built in tail call optimization because we have this accumulator. If we didn't have this accumulator, there are ways to write this without the accumulator, and if you do it, then for big enough numbers it would fail. And however big that number is, that would just completely depend upon where you were running it and all of the environment that you were running it in. But there you have it. Much simpler than yesterday. We've got an isMultiple function, we've got a 3 or 5 multiple function, and we got our solve function using a little bit of recursion. But you see, it's actually, you can write it in many fewer lines of code than what we wrote it in yesterday. Both still purely functional. I'll leave it to you to decide which one you like better. This one is obviously going to be more optimized than the previous one, from the standpoint that we're only having to do, let's say you put in 1,000 here, you're only going through 1,000 once. Rather than yesterday, we created a list of 1,000 and iterated through that list potentially twice. So there you have it. Episode 49, Solving Euler with number 1, this time with recursion. Thank you.